In part 1 of this video series, we discussed how neurons generate, propagate, and pass action potentials. In this second part, we are going to take a look at how neurons repolarize. More specifically, we looked at the material that allowed us to understand the first half of this graph. And now, when we look at repolarization, it will allow for us to understand the second half of this graph. And then we can put it all together. Just in case you missed it, the link to the first video is located on the screen as well as within the description. What we saw at the end of part 1 was that all throughout the axon and axon terminals, the interior was positive 30. As the action potential travels from the hillock down the axon into the terminals, every interior region ends up being approximately positive 30 millivolts. And now what needs to happen is every single one of these regions needs to get back to negative 70 millivolts. In order to move from positive 30 back towards negative 70, that is referred to as a repolarization. And that is what we are going to take a look at. This repolarization is necessary so that the neuron can then generate another action potential. And as I stated in the prior video, some neurons can generate well over 1,000 action potentials per second. So it is essential that every single one of these regions return to at least close to the resting membrane potential. And what we are going to look at specifically here is we're going to look within the axon hillock. We are going to look at how the axon hillock repolarizes, and that will then allow you to see how every single one of these regions repolarize because it is all identical. So let's go ahead and draw the axon hillock. Okay? And remind ourselves, how did we get to positive 30 millivolts inside of the hillock in the first place? Well, inside of the hillock, to start off with, the membrane potential, the resting membrane potential, would be negative 70 millivolts, just like it is everywhere else within the neuron. And what needs to happen is we need to depolarize the hillock region from negative 70 to negative 55, which is what's called threshold. Right? We need to make the hillock region interior 15 millivolts more positive. The way that happens is that a presynaptic neuron will release excitatory neurotransmitters onto this neuron, right, called the postsynaptic neuron, and those excitatory neurotransmitters will allow for sodium to enter into the different dendritic regions of this neuron, the postsynaptic neuron. Sodium coming into those dendritic regions would depolarize those dendritic regions, make the interior of those dendritic regions more positive. Those depolarizations would then begin to move towards more negative areas within the neuron, meaning those depolarizations would move down the dendrites towards the cell body and ultimately towards the axon hillock. Now, these depolarizations, which are really little waves of positivity moving towards the hillock, they fall apart as they move towards the hillock, meaning that they become less and less positive or more and more negative as they move away from the point of origin. So technically, they're referred to as graded potentials. Many factors go into this, but the objective is for these graded potentials to stay as positive as possible as they're moving towards the hillock. Or you can think about that as we want them to decrement as little as possible. There are many factors that will influence that, which is covered in another video on graded potentials that focuses on temporal and spatial summation. Anyways, if these waves of positivity, these depolarizations, don't fall apart too much, then by the time that they get to the hillock region, they'll still be carrying essentially enough sodium ions positivity to depolarize the Hillock region from -70 up to -55 millivolts. And that will cause voltage-gated sodium channels within the plasma membrane of the Hillock to pop open, and that then will serve as a passageway for sodium ions within the interstitial fluid to move from the interstitial fluid into the intracellular fluid or cytosol of the axon hillock. And these sodium ions come in through both a chemical and electrical driving force because the interior is -55, and as they enter into the hillock is gaining positively charged ions, so of course the hillock depolarizes, and it depolarizes all the way up to +30 millivolts. And the question is, why do we stop at +30? Because in the video where I cover the resting membrane potential, it is established that sodium has an equilibrium potential within neurons of +60. So logically, there's not a real reason why +30 should be where this stops. It seems kind of arbitrary. So why all of a sudden does the membrane potential freeze at +30 millivolts in the hillock? The answer is these voltage-gated sodium channels within the plasma membrane of the hillock are not as simple as they appear. So these voltage-gated sodium channels, when the interior gets to -55 millivolts within the hillock, as the hillock depolarizes by 15 millivolts and we hit threshold, when the voltage-gated sodium channels open up, what actually opens up is something known as an activation gate. We're going to look more closely at this, at a better drawing of this in just a moment, but this is an incredibly important part. What opens within the voltage-gated sodium channels are their activation gates. And that activation gate opening up means that the voltage-gated sodium channel opens. And that then allows for sodium ions to come in and drive the interior from -55 millivolts up to +30 millivolts. And then when +30 is hit, something else happens with the sodium channels. At +30 millivolts, the sodium channels, the voltage-gated sodium channels, close. But it's not as simple as saying that their activation gates just close. That's actually not what happens at all. At +30 millivolts, what closes on the voltage-gated sodium channels are another gate, which is referred to as an inactivation gate, which I'm drawing in red there. Okay. So at +30 millivolts, the voltage-gated sodium channels shut, but more specifically, what shuts on the voltage-gated sodium channels are their inactivation gates. And if the inactivation gates close, then no more sodium ions can enter. Right? And if no more sodium ions can enter, then it makes sense how the interior gets stuck at +30. Because there's no more influx of positively charged sodium ions, so the inside can't become any more positive. So let's, for a moment, look at a drawing of these sodium channels, and hopefully you'll get a better idea of what I'm talking about. Imagine this as being the plasma membrane of the hillock. Okay. Inside of the plasma membrane of the hillock are these voltage-gated sodium channels. Now, when the interior is at -70 millivolts, the voltage-gated sodium channels are closed, but more specifically, the activation gates are what are closed. And that's preventing any of these sodium ions from being able to come in. But if we can depolarize the hillock region on the interior from -70 millivolts up to -55 millivolts, then threshold is hit, and that change in the voltage is what causes the voltage-gated sodium channels, specifically the activation gates, to open up. And once the activation gates are open, then the voltage-gated sodium channel, the passageway through it is open. And now all of a sudden, these sodium ions within the interstitial fluid can move from the interstitial fluid through the voltage-gated sodium channels into the intracellular fluid of the axon hillock and depolarize it to +30 millivolts. But then, at positive 30 millivolts, we have said that the voltage-gated sodium channels close. But more specifically, what closes, if you take a look over here, what closes is the inactivation gate, right? You can see that the inactivation gate is not the same thing as the activation gate. The inactivation gate is a different gate that closes at positive 30 millivolts. And what it does is it prevents any more sodium from coming from the interstitial fluid through the voltage-gated sodium channel and into the intracellular fluid. And that would prevent the interior from becoming any more positive. So we're stuck at positive 30 millivolts. For the moment, it may sound like the difference between this activation and inactivation gate isn't all that important, but it's actually incredibly important for understanding the overall function and purpose of repolarization and of what will ultimately be a discussion of refractory periods. So let's try and draw this again. Here is the axon hillock. Within the plasma membrane of the axon hillock are these voltage-gated sodium channels. If we can depolarize the hillock region from -70 to -55 millivolts, meaning if we can depolarize it to threshold, then specifically in green, what will open up are the activation gates on the voltage-gated sodium channels. Right? So threshold is hit and activation gates on the voltage-gated sodium channels open, and that then allows for sodium to travel through both a chemical and electrical driving force into the hillock region and depolarize the hillock region from -55 to positive 30 millivolts. Now, at positive 30 millivolts, the voltage-gated sodium channels are going to close, but when the voltage-gated sodium channels close in red, what's actually closing are the inactivation gates. So at positive 30 millivolts, the inactivation gates on the voltage-gated sodium channels shut, and that is what prevents any more sodium from being able to enter in, and why the interior of the hillock is stuck at positive 30, because it's not gaining any more positively charged sodium ions. So that's great that we're stuck at positive 30, but how are we going to start getting back towards a negative value, like towards -70? So I'm going to draw a bigger image of the hillock here. And in black are the voltage-gated sodium channels. And if the interior is at positive 30, then what do these voltage-gated sodium channels look like? Well, their inactivation gates in red are closed. So the inactivation gates on the voltage-gated sodium channels are closed, and that's preventing any sodium from being able to come through them, into the interior of the hillock, which is why it's stuck at positive 30. And at the same time, the activation gates in green are actually still popped open. All right, so that's how the voltage-gated sodium channels look at positive 30. But something else happens at positive 30. At positive 30, there's another type of voltage-gated channel. And this voltage-gated channel is what's called a voltage-gated potassium channel. At positive 30, not only do the voltage-gated sodium channels in black close due to their inactivation gates shutting, but at the same time, at positive 30 millivolts, voltage-gated potassium channels open up. And what do we know about potassium? Potassium is high inside of neurons, and potassium is low outside of neurons. Additionally, what does potassium actually have right now? If the interior of the hillock region is positive 30, then the outside, right, within the interstitial fluid of the hillock, it has to have a slight negative charge to it. It's probably close to -30. So potassium actually doesn't just have a chemical driving force to leave. Right now it has something that it usually doesn't, which is also an electrical driving force to leave. The outside of the hillock region is actually negative right now, right, within the interstitial fluid. So if you open up voltage-gated potassium channels, then potassium wants to leave the cell not only through a chemical, but also an electrical driving force, and that is exactly what it is going to do. And if potassium is leaving, what is the helic losing? If potassium is leaving the helic, then the helic is losing on the interior positively charged ions, right? Positively charged potassium ions. So the proportion of negatively charged ions is rising in the interior compared to the number of positively charged ions because it's losing positively charged potassium ions to the exterior of the cell. And thus, that means that the interior is going to begin to become more negative, right? This efflux, as it's called, of potassium ions causes the interior of the helic to begin to become more negative. This is the beginning of what's referred to as repolarization. This efflux of potassium ions through these voltage-gated potassium channels is what causes repolarization, the movement of the interior back towards a negative value. Repolarization is when the interior becomes more negative. Depolarization is when the interior, of course, becomes more positive, as we've discussed a variety of times. So let's take a look at a drawing of this. Every textbook will draw this a little bit differently or display it a little bit differently, but this would be like the voltage-gated potassium channel. Okay? You'll notice that there's really, in this image, there's not an inactivation gate and an activation gate. All we would say about the voltage-gated potassium channel is that it's either open or it's closed. And when the interior of the helic depolarizes to positive 30 millivolts, two things are going to happen, right? First of all, the voltage-gated sodium channels at positive 30, their inactivation gates are going to close and no more sodium is going to come in. Number two, these voltage-gated potassium channels at positive 30 are going to open. You can see that they have opened up, and what that does is it allows potassium to move from the inside of the helic to the outside of the helic. It allows potassium to follow its chemical and electrical driving force from the inside to the outside. Basically, another way of saying this is that at positive 30, the permeability for potassium within the helic region, the plasma membrane of the helic region, increases. Right? So potassium doesn't just have leak channels it can travel through, but it has these voltage-gated potassium channels now that it can travel through as well. And that's really going to ensure that a lot of potassium can move from the interior of the helic to the outside. And if the interior is losing positively charged potassium ions, it's going to begin to become more negative on the inside, and repolarization can occur. So let's discuss repolarization some more and why the structure of the voltage-gated sodium channels is actually so important. So at this point in time, let's say that repolarization is happening. In black are, again, those voltage-gated sodium channels. During repolarization, how are they organized? Well, their inactivation gates in red are closed. This is, again, during repolarization. And during repolarization, their activation gates in green are open. Right? So that's the structure of the voltage-gated sodium channels during repolarization. Inactivation gates closed in red, activation gates open in green. And at the same time, during repolarization, we know that voltage-gated potassium channels are open. And what purpose are the voltage-gated potassium channels serving? They are allowing potassium to move through them, right? And potassium is moving from inside to outside of the cell. Right? It's moving from down its chemical and electrical driving force from the intracellular fluid into the interstitial fluid, and since the interior of the helic is losing positively charged ions, the interior is repolarizing, and it's becoming, which means that it is becoming more negative. Now, let's say that the interior repolarizes from positive 30 all the way back down to negative 55 millivolts. What technically happens at negative 55 millivolts? Negative 55 millivolts is technically threshold. So what technically should occur at negative 55 millivolts is the voltage-gated sodium channels should technically open again, which would not be good. Because if we're repolarizing and we hit negative 55 millivolts and the voltage-gated sodium channels open up again, that then would allow for sodium to shoot in and essentially drive another action potential to occur. So you would end up with basically a repetitive loop of action potentials, which is not what the neuron wants. It's not anything that would make any sense in the human body, and it would not be sustainable. Every single time that the neuron repolarizes back to negative 55 millivolts, you wouldn't want another action potential to happen. But luckily, these voltage-gated sodium channels don't open when the interior repolarizes to negative 55 millivolts. And the reason that they don't open is because in red, what's actually closed on them is their inactivation gates. And those inactivation gates do not open under a voltage. They stay shut at negative 55 millivolts. They are believed to be timed, meaning that a voltage is not what's going to open them. So just because the interior gets to negative 55 millivolts during repolarization does not mean that the voltage-gated sodium channels are going to pop open again just because you've technically gotten to what is the threshold value. And what can happen is the interior can keep repolarizing beyond negative 55 millivolts, and that's exactly what happens. It begins to repolarize back towards negative 70 millivolts. And as you're going to see, it's actually going to go beyond that. It's going to do something which is known as a hyperpolarization. It's going to hyperpolarize. It's going to become more negative than the resting membrane potential. But before we get to that, something's going to happen somewhere between like negative 56 and negative 70 millivolts, and this is going to vary from one neuron to the next exactly when this happens. But somewhere between negative, again, like 56 and negative 65, negative 70, what occurs is the voltage-gated sodium channels reset. What that means is between, again, like I said, let's just say negative 56 and negative 70. There's a pretty big possible range there. But regardless, these voltage-gated sodium channels at that point are going to reset. That means if you were to take a look at them, let's draw a picture of one. Let's say that this is one. It would mean that the inactivation gate is going to pop back open, and the activation gate is going to close. So I was drawing in red the inactivation gate opening up and the activation gate closing. Let's look at a drawing of that. So this would be the structure of the voltage-gated sodium channel during repolarization. You can see, I'll draw in red, the inactivation gate is closed. And actually the activation gate is in fact open. So when we are repolarizing, potassium is leaving and the interior gets to negative 55 millivolts during repolarization. The voltage-gated sodium channel doesn't close because the inactivation gate is shut and it won't open up under a voltage. But once we continue repolarizing, negative 56 and beyond, let's say between negative 56 and negative 70, as I said, big variance between neurons, what will happen is this channel will fully reset, meaning the inactivation gate will pop back open and the activation gate will close again. And again, this is happening somewhere between negative 56 and negative 70, we'll say. And what does this actually mean? Like, if the voltage-gated sodium channels have now reset, and what's closed is in fact the activation gate and not the inactivation gate, then somehow if we were to depolarize back to threshold again, then the voltage-gated sodium channels would be able to open, and sodium would be able to come in, and another action potential would be able to occur. This is going to be relevant for understanding the action potential graph, and even more importantly for understanding what's coming next after this whole discussion in another video, which is refractory periods. But for the moment, the inactivation gate being closed during repolarization is what prevents the voltage-gated sodium channels from opening when the threshold value is hit, because the inactivation gate doesn't open up under a threshold. And then somewhere in the range of -56 to -70, the voltage-gated sodium channel resets, meaning that the inactivation gate opens while the activation gate closes. And at this point, technically, if the interior could get back to threshold, essentially meaning if enough sodium could get into the Hillock region to depolarize it to threshold, then another action potential could in fact occur. So now let's draw the Hillock during this phase of repolarization. So these would be, again, the voltage-gated sodium channels. This is going to be repolarization between like -56 and -70. What has happened? The voltage-gated sodium channels have reset, meaning in red, their inactivation gates have popped back open. And their activation gates have closed. This is back to the organization of the voltage-gated sodium channels from the first video, meaning that simply, if you can now depolarize the Hillock region to threshold, the voltage-gated sodium channels technically will open again, and another action potential will be generated. You'll see later on in a different video that is harder to accomplish, but it can happen. So also, what's happening during this period of time, as you know, repolarization is occurring, so the voltage-gated potassium channels are open, and potassium, I'm going to draw that in black instead, and potassium is leaving the inside of the Hillock for the outside of the cell. That's causing repolarization to continuously happen, right? And we're repolarizing back towards -70. Now, the logical conclusion might be, okay, at -70 millivolts, that must be when the voltage-gated potassium channels close, and then maybe some sodium-potassium pumps could kick some potassium back in and sodium back out, and everything would be back to normal. But that's actually not what happens. When we get to -70 millivolts, the voltage-gated potassium channels actually stay open. They don't close once it is returned to the resting membrane potential value. And this part, well, many parts of this tend to confuse people, but this one really tends to get a lot of people in terms of confusion. Why, at -70 millivolts, which is the resting membrane potential, don't the voltage-gated potassium channels close? And why does the voltage-gated potassium channel staying open cause a hyperpolarization? Meaning, why does this cause the interior to actually become more negative than -70? To fully appreciate and understand this, a basic understanding of the resting membrane potential is required. I have a video on that, which is linked in the description, which you're certainly, I would recommend that you watch. Although you can try to comprehend this without it if you like. So at -70 millivolts, that is technically the resting membrane potential. At -70 millivolts, the rate at which potassium leaves through its leak channels is the same rate that sodium comes in. Now, the leak channels would be embedded everywhere, all throughout the axon terminals, buttons, cell body, dendrites, right? That's what allows for the resting membrane potential to exist. So those leak channels are everywhere. And at -70, potassium theoretically should be leaving through those leak channels at the same rate that sodium is coming in. through the leak channels. So we should be stuck at -70. But here's the thing. You don't just have leak channels in the plasma membrane right now for potassium. Let's draw those leak channels, like I said. Let's actually draw them in green. These would be the leak channels. These are the regular old leak channels that potassium can leave through. What also do you have right now during repolarization at -70? You don't just have the leak channels open. You've got the voltage-gated potassium channels open. There are more channels for potassium to leave through right now than it normally has. At -70, typically potassium would only have the leak channels to leave through. But now, during repolarization at -70, it has the leak channels to leave through, and it also has the voltage-gated potassium channels that it can leave through. So it has potassium leak channels to leave through, and it's got all of these different voltage-gated potassium channels to go through. So it can go through all of these different channels. And why would this allow for the membrane potential to hyperpolarize, actually become more negative than the resting membrane potential? And the answer to that is because the rate at which potassium can leave right now is increased because there's more doors for it to travel through. There's an analogy that I can give you here that I think is somewhat helpful. Imagine you have two stadiums. Each stadium has 50,000 people within it. Okay? If there's 50,000 people in the first stadium, and there is, imagine people and potassium ions are the same thing. There's 50,000 people in the stadium, like there'd be 50,000 potassium ions in the stadium. And then imagine that there's 100 doors they can leave through. Okay, the game is over and everybody's leaving. So there's 50,000 people, 50,000 potassium ions with 100 doors or 100 channels to leave through. The channels or the doors are going to dictate the rate at which the people or the potassium ions can leave. Right? If there's only 100 doors for people to leave through in the stadium, that means that the rate at which the people can actually leave the stadium is dictated partly, of course, by the doors, the number of doors in the stadium. Okay? So now compare it to the stadium, the other stadium that we're discussing. This other stadium has 50,000 people in it as well. But that stadium has 200 doors. If there's 200 doors in the other stadium, there's 50,000 people in it, just like the first stadium, but there's 200 doors. Again, say that there's 50,000 potassium ions, but now 200 doors for those potassium ions to leave through. Which stadium is going to empty faster? Everybody, I think, knows that a stadium with 200 doors in it is going to empty faster than a stadium with 100 doors in it. The reason that it empties faster is because the rate at which the people can leave, or the potassium ions can leave, is greater if there's more doors for the people or the potassium ions to leave through. Again, Stadium 1 has 50,000 people in it, only 100 doors. Stadium 2 has 50,000 people in it, 200 doors. The rate at which the people can leave in Stadium 2 is significantly greater. It's going to empty faster. Right now, inside of the axon hillock, the membrane potential is -70 millivolts. Usually, at this value, potassium would only have a particular number of leak channels it could leave through. But because the voltage-gated potassium channels are still open at -70, it doesn't just have the leak channels it can leave through, it has the extra voltage-gated potassium channels it can leave through. So the hillock region is much more permeable to potassium at -70 right now than it normally would be at -70 because these voltage-gated potassium channels are open. And what that means is since potassium has more channels that it can leave through than normal at -70, the rate it can leave at is greater. Right? It's got more passageways, more doors it can travel through. So the rate at which potassium can leave at -70 millivolts is much greater than it normally would be. And what all of this means right? This is like the potassium ions right now are behaving like the stadium that has 200 doors in it. Since there's more doors, the people or the ions, they can leave faster. The rate at which potassium or the people can leave is greater. Okay, so there's more doors, potassium is leaving at a greater rate. That means at negative 70, since potassium is leaving at a greater rate than it normally would because of these extra doors, it's still leaving at a greater rate than sodium is coming in through its leak channels. And if potassium is leaving at a greater rate than sodium is coming in at negative 70, usually it wouldn't be, but because of these extra channels being open, it is. Then the interior is still losing more positively charged potassium ions than it's gaining in positively charged sodium ions, and the interior is going to keep becoming more negative. So the interior will repolarize beyond negative 70 millivolts, and when that happens, it's called a hyperpolarization. The interior hyperpolarizes, becomes more negative than the resting membrane potential, and let's say that it repolarizes to about negative 75 millivolts or so. And for whatever reason, we'll actually discuss why in a second here, when you get to negative 75, all of a sudden it stops. You get to negative 75 millivolts and the interior doesn't become any more negative. Why would that be the case? So now we can draw and really start to see the entire picture. So right now, we would be, let's take a look at the Hillock region right around negative 75-ish. These would be the voltage-gated sodium channels. The voltage-gated sodium channels would be just like they were the last time we spoke about them. So the inactivation gates in red would be open, right? These are going to be completely reset. And the activation gates in green would be closed. And just for the moment, these are the voltage-gated potassium channels. We're going to say that they're still open. Okay. So potassium is shooting out of these voltage-gated potassium channels, and it's also leaving through the leak channels, by the way. By leaving not just through the leak channels, but also through the voltage-gated potassium channels, that's what's allowing for potassium to continue to leave at a greater rate than it normally would at this particular voltage. Particularly like last time at negative 70, potassium's leaving at a greater rate at negative 70 than it normally would be because it has more channels to be able to leave through. So it's still leaving at a greater rate than sodium is coming in. So the cell is still actively losing, or the Hillock region specifically is still actively losing positively charged potassium ions, more positively charged potassium ions than it's gaining in sodium ions. So it's continuing to become more and more negative. And then why at negative 75 millivolts does it all stop? And the answer is, well, because finally these voltage-gated potassium channels close. The voltage-gated potassium channels finally shut at negative 75 millivolts, so all that extra potassium that was leaving, meaning the extra rate at which potassium was leaving because of the voltage-gated potassium channels being open, that stops because the voltage-gated potassium channels close. And now all potassium has to leave through is its leak channels. And because of this, what's going to happen is actually the interior of the hillock is going to slowly, it's not that slow, but it's going to depolarize. It's going to become more positive, and it's actually going to move back up to the regular resting membrane potential. And this takes a little bit of explaining as well. Why, when the voltage-gated potassium channels close? I think it makes sense, hopefully, that when the voltage-gated potassium channels close at negative 75, now potassium doesn't have these extra channels to leave through, so the rate at which potassium can leave is decreased, and thus the cell kind of gets stuck at negative 75. But what about that would cause the interior to actually depolarize a little bit back to the resting membrane potential? This is probably the most challenging thing to understand and also explain, so bear with me. It really involves the application of many challenging concepts related to neurons. But what would be happening right now at negative 75 would be that these are the voltage-gated potassium channels. The voltage-gated potassium channels at negative 75, as we have discussed, the voltage-gated potassium channels close. And the question is, does potassium still have anything that it can leave through? And the answer is yes, it does. In purple, these are going to be the potassium leak channels. So there are still leak channels that potassium can leave through. And it's going to leave through them because negative 75 is negative, right? It's quite negative, but that's still not potassium's equilibrium potential. Potassium's equilibrium potential is around negative 94 millivolts. So as a consequence, if there are leak channels for potassium to leave through, you better believe it's still going to leave because its chemical driving force to leave is greater than its electrical driving force pulling it back. That said, right now we're at negative 75 millivolts. And we've returned to the standard permeability that potassium usually has during the typical resting membrane potential. Meaning that all those extra potassium channels, the voltage-gated potassium channels, shut. And now all potassium has to leave through are the leak channels. So you're back to the standard permeability that typically exists during the resting membrane potential, but you're actually more negative than the standard resting membrane potential, right? It's negative 75. So you have the standard permeability of what you usually see during the resting membrane potential, yet the interior has hyperpolarized. It's more negative than normal. What effect would that have on potassium? It would pull the potassium ions backwards through this negative electrical driving force more strongly than typical. So right now, potassium is actually going to be leaving at a lower rate. It's going to be leaving at a reduced rate compared to what it typically would be at the resting membrane potential. It has to be, right? Because the interior is negative 75. We have a hyperpolarization. And right now, the same number of leak channels for potassium are open as would be during the resting membrane potential of negative 70, but we're actually at negative 75. So since we're at negative 75 rather than negative 70 with the same number of potassium leak channels as usually and is always there, then potassium's actually going to be leaving at a reduced rate compared to what it normally would be at negative 70. That's number one. It's rather confusing, but work through that a variety of times, and I hope it'll make some sense. Now let's factor in sodium into the equation. We know that there are some sodium leak channels. I'll draw 3 of them here for us. And we know that sodium comes in through these leak channels. Right? Sodium is high on the outside, it's low on the inside, right? So it has a chemical driving force to enter, an electrical driving force to enter. And at the standard resting membrane potential of negative 70 millivolts, sodium is coming into the cell at the same rate that potassium is leaving. Right? That's what happens at the resting membrane potential. At negative 70 millivolts, potassium exits at the same rate that sodium enters. The interior has become negative enough that it's pulling potassium backwards and pulling sodium inwards at such a rate that potassium actually exits at the same rate that sodium comes in. But right now, we're at the standard permeability for potassium to sodium. Right? The cell is much more permeable to potassium than it is to sodium regardless, but we're at that regular old permeability. All we've got open are potassium and sodium leak channels, but the inside is negative 75 because we hyperpolarize to negative 75. So if we're at negative 75 with the standard permeability that we usually see during the resting membrane potential, then what's going to happen? Potassium is being pulled back more strongly than it normally would be, and sodium is being pulled in at a greater rate than it normally would be at negative 70. That's what I keep meaning by it normally would be. If it at negative 70, potassium would be being pulled back at such a rate and sodium being pulled in at such a rate that potassium would leave at the same rate that sodium is coming in. But now we're in that exact same situation, except meaning we have the exact same permeability for potassium and sodium, except the interior is negative 75. And if the interior is negative 75, that's a greater negative electrical driving force. And what that's going to do is it's going to pull potassium backwards to a greater rate than normal, and it's going to pull sodium inwards to a greater rate than it normally would. So what that actually means, when you break it all down, is if we're at negative 75 right now, with the standard permeability that we see during the regular resting membrane potential, then sodium is actually going to be entering the cell, the hillock region, at a greater rate than potassium is going to be leaving. Right? At negative 75, this has to be true, because usually at negative 70, that's the resting membrane potential, potassium leaves at the same rate that sodium comes in. But right now we're at negative 75. What effect would making the interior more negative, which has happened, have on these ions? It would pull potassium ions backwards to a greater degree and would pull the sodium ions inward to a greater degree. And if potassium is leaving at a lesser degree and sodium to a greater degree because of this more negative interior, hyperpolarized interior, then actually sodium would be entering now at a slightly greater rate than potassium would be leaving. That has to be true if you have the standard permeability that results in a resting membrane potential of negative 70, meaning at that value potassium leaves at the same rate that sodium comes in, and you keep that standard permeability yet make the interior even more negative, so that potassium leaves at a lesser rate than it would at negative 70 and sodium enters at a greater rate than it would at negative 70. That's going to mean that sodium is going to enter at a greater rate overall than potassium is going to leave. And now the interior is going to be gaining positively charged ions. Right? It's going to be gaining more sodium than it's losing in potassium, and the interior is going to be gaining as a net positively charged ions, and that's actually going to cause it to depolarize. It's going to cause it to become more positive. And as it becomes more positive, it'll keep depolarizing from negative 75 until it gets back to negative 70. And once it gets back to negative 70, now you have truly returned to the resting membrane potential. Because as the interior becomes a little bit more positive, as it moves from negative 75, as it moves from negative 75 to negative 70, the interior is becoming more positive. And as the interior becomes more positive, uh, meaning that it moves from negative 75 to negative 70, the pull for sodium to come in won't be quite as strong, and the pull for potassium to be pulled backwards won't be quite as strong. So as the interior moves from negative 75 to negative 70, basically that will slightly decrease the rate at which sodium is entering, and it will slightly increase the rate at which potassium leaves. Right? If you make the interior more positive, the pull for potassium to come backwards won't be as strong, so a little bit more potassium will leave, and the pull for sodium to come in won't be as strong, so not as much sodium will enter. And then finally, when you get back to negative 70 and you have this regular old permeability here that you usually have, you're truly back to the resting membrane potential. You'll be back to the point at which potassium leaves at the exact same rate that sodium comes in. And now the hillock is back to resting at negative 70 millivolts. Right? You're back now to the true resting membrane potential. Potassium is leaving through the leak channels at the same rate that sodium is coming in through the leak channels. There's only one last thing to consider. And that last thing to consider is what happened with regard to sodium and potassium. During the action potential, what came in through the voltage-gated sodium channels was sodium. Sodium ions came in through the voltage-gated sodium channels that drove the interior up to positive 30 millivolts. Then what happened is essentially potassium shot out. Potassium shot out of the cell, the hilic region, and that was then able to repolarize the interior back down. It actually hyperpolarized it all the way to -75, but nonetheless, it repolarized the interior so that the interior could get back to -70 millivolts. So what happened is the cell, the hilic region, and every other region of the axon, it gained some sodium on the interior and lost some potassium on the interior. And that can't happen for too long. So what definitely needs to be embedded into the plasma membrane of the hilic and every other region of the axon is a pretty high concentration of of sodium potassium pumps. Now, these are going to be everywhere throughout the neuron to ensure that the resting membrane potential is maintained, but they're especially going to be concentrated in the axon terminal regions, because you can see how the membrane potential, as it changes, how it gains sodium and then the interior loses potassium. So what these sodium-potassium pumps do, the type of primary active transport, is they utilize ATP in order to continuously kick potassium back in against its concentration gradient and kick sodium back out against its concentration gradient. And what that does is it ensures that on the inside of the hilic and throughout the axon terminals, that intracellular potassium stays high and intracellular sodium stays low. The sodium potassium pumps will become very active, really kind of right away, but especially during the latter half of repolarization. They're going to start working very hard to ensure that any potassium that was lost is returned to the interior and any sodium that was gained is returned to the exterior. And at this point, now we are truly back to where everything started. Right? We're at the resting membrane potential of -70. We've got all the potassium inside that we normally do. We've got all the little amounts of sodium inside that we normally do. The voltage-gated sodium channels are closed. Their activation gates are shut. Their inactivation gates are open, meaning that if we get to threshold, then if we get the interior of the hilic from -70 to -55 millivolts to threshold, then the voltage-gated sodium channels can open, and we can get another action potential. The voltage-gated potassium channels are shut too right now, so that they can open up at +30 and repolarize us back to the regular resting membrane potential when and if need be as well. So everything is back and ready to go at this point. Once the final thing to discuss was the sodium potassium pumps, ensuring that these concentrations of sodium and potassium don't shift too much as these action potentials and repolarization occurs. Now, this exact same process is going to play out in every region of the axon and axon terminals, right? As every region becomes +30 millivolts, this same process of repolarization will play out in every single one of these regions, meaning the inactivation gates closing and the potassium channels opening and hyperpolarization, and all of that is going to take place in every single one of these regions to return every single one of these regions to -70 millivolts. And now the entire axon terminal would be back to where it normally is, and another action potential can happen. And it's essential that this whole process play out because, as I've said in the past, some neurons can generate over 1,000 action potentials per second. And if you want them to generate 1,000 action potentials per second, then every time the interior gets to +30, it has to return back to -70. So it's really incomprehensible how quickly all of this actually plays out. It takes hours to go through all of it in your head, but yet the neuron is capable of doing it in milliseconds. So it's quite amazing. So now with all of the information from the first video and the information from this video, we can make sense of perhaps the most confusing graph in all of human physiology. And that is this graph. So what is it showing exactly? You have to remember what it's depicting is really the axon hillock. Okay, technically it could be any portion of the axon, but let's call it the hillock. Inside of the hillock at rest, the resting membrane potential is negative 70 millivolts. That's what's being depicted right here. And if we can depolarize the hillock region from negative 70 to negative 55 millivolts, if we can depolarize it by 15 millivolts, then we will hit threshold, which you can see, right, is right there. Okay, so we depolarize the hillock region by 15 millivolts, threshold is hit, and at threshold, what happens? Voltage-gated sodium channels, specifically voltage-gated sodium channels activation gates, open up at threshold. What that does is, if at threshold the voltage-gated sodium channels activation gates open, then sodium is able to rush in through its chemical and electrical driving force into the interior of the hillock region, and the influx of sodium ions, which are a positive ion, drives the interior all the way up to positive 30 millivolts, which is depicted here, right, in the graph. The interior of the hillock rises to positive 30 millivolts. And at positive 30 millivolts, two other important things are about to happen. First of all, the voltage-gated sodium channels inactivation gates, which I'm showing in red here, close. So the inactivation gates on the voltage-gated sodium channels shut, and that prevents any more sodium from being able to enter. That's part of the reason why we get stuck at positive 30 millivolts. And the next thing that occurs at positive 30 millivolts is the voltage-gated potassium channels are also about to open, or do open. So at positive 30 millivolts, the voltage-gated sodium channels shut, specifically the inactivation gates close. Additionally, at positive 30 millivolts, the voltage-gated potassium channels open. And what do we know about potassium? Potassium is high inside of the cell. It's low outside of the cell. So it has a chemical driving force to leave. And the interior is positive right now, and the exterior would then be slightly negative, which means that potassium doesn't just have a chemical driving force to exit, it also has an electrical driving force to exit. And that's exactly what it's going to do. It's going to follow its chemical and electrical driving force out of the cell. And as potassium exits the hillock region, it's going to cause the hillock region to repolarize. It's going to cause the hillock region to become more negative. Why would that be? Because potassium is a positively charged ion and it's leaving the interior of the hillock. So the hillock is actively losing positively charged potassium ions. It's losing positively charged ions. So the interior is going to be becoming more negative. And very importantly here, when the interior repolarizes to negative 55 millivolts, what we see is that at negative 55 millivolts, which is threshold, technically that's the threshold value, we see that the voltage-gated sodium channels don't open, because they technically should open at that threshold value, but they don't. And the reason for that is because of the fact that the inactivation gates on the voltage-gated sodium channels are closed. And the inactivation gates on the voltage-gated sodium channels, they don't open under a threshold voltage. So as the interior of the hillock moves from positive 30 back down towards negative 55 millivolts, thanks to the efflux of potassium ions through the voltage-gated potassium channels, when we get to negative 55, the voltage-gated sodium channels do not open. The inactivation gates prevent that from occurring and ensure that another action potential does not immediately happen. All right, so let's continue on from there. What happens next is that potassium is going to continue to leave through these voltage-gated potassium channels. And as potassium continues to leave through these voltage-gated potassium channels, the interior continues to repolarize. And then I said somewhere between -56 and -70, what's going to happen is the voltage-gated sodium channels are going to reset. What that looks like is the voltage-gated sodium channels would have those inactivation gates pop open, and their activation gates would close. What this means is if the voltage-gated sodium channels reset and their inactivation gates open and their activation gates close, that means that if we could get the interior of the hillock back to threshold, the voltage-gated sodium channels would in fact open again and we could have another action potential. All right, so one would think once we get back to -70 millivolts, everything would return to normal, but it in fact is not. When we get to -70 millivolts, which is approximately right here, the interior keeps becoming more negative. It hyperpolarizes. The interior actually goes all the way down to like -75 or so. So why does the interior hyperpolarize of the hillock? Why does it become more negative? And the answer is the voltage-gated potassium channels stay open. So at -70, what happens is the voltage-gated potassium channels are open, and additionally, there would be leak channels for potassium in the membrane as well. So at -70, this would typically be the resting membrane potential. Basically, potassium would be leaving through the leak channels at the same rate that sodium would be coming in through its leak channels. But at -70 right now, it's not just leak channels that are open. There are also voltage-gated potassium channels that are open. So since the voltage-gated potassium channels stay open, potassium doesn't just have leak channels it can leave through, it has voltage-gated potassium channels it can leave through. So there's basically extra potassium permeability at -70 than there normally would be. And the analogy that I used earlier on, if there are extra passageways or doors for potassium to leave through, then it's going to leave at a greater rate. It's going to leave the cell at a greater rate at -70 than it normally would. And it's going to be leaving since it's leaving the cell at a greater rate than it normally would be at -70, it continues to leave at a greater rate than sodium enters through its leak channels. So if potassium at -70 is leaving at a greater rate than sodium is entering, and this is thanks to the extra open voltage-gated potassium channels allowing potassium to leave at a greater rate than sodium is entering, then the interior will continue to become more negative because there's a continued net loss of positively charged ions, right? Potassium is leaving at a greater rate than sodium is entering, and thus the interior is going to continue to become more negative and hyperpolarized. And then finally, we hit -75 millivolts. And it stops. Why does it stop at -75 millivolts and not become more negative? The answer to that is that finally at -75 millivolts or so, the open voltage-gated potassium channels close. And now those extra channels that potassium had to leave through are gone. And potassium at this point can now only leave through its leak channels. So the rate at which potassium can leave at -75 is reduced due to the fact that the voltage-gated potassium channels close and the total number of channels that it has to leave through is reduced, which reduces the rate at which it can leave. So potassium doesn't leave at a greater rate than sodium enters anymore, so of course the interior can't become any more negative. And then we get to what is the most conceptually challenging part of this, which is why after we repolarize to -75 millivolts, do we then depolarize back to negative 70 millivolts, which is the resting membrane potential. And I would recommend, if you need a review of this, to just rewind the video a little bit. But the simple answer, there's no simple answer to this, but the simpler answer that I can give for the moment is that what happens is at negative 75 millivolts, the extra voltage gated potassium channels, they close. These voltage gated potassium channels shut. So the extra channels that potassium had to leave through at negative 70 just a little bit ago, they're gone, right? They've shut. And now the only channels that potassium has to leave through are the leak channels. So that by itself is going to slow down the rate at which potassium can leave, because, well, if you close doors or channels that potassium can exit through, then it has less channels it can leave through, and that's going to decrease the rate at which it can leave. And additionally, you've made the interior more negative than it normally would be at the resting membrane potential. You've made it negative 75. And that is going to slow down the rate at which potassium can leave, because you're pulling the potassium ions backwards to a greater degree. So once those extra potassium channels close and the interior is negative 75 millivolts, the rate at which potassium can leave is decently reduced. And if you think of sodium, on the other hand, sodium still has, the couple leak channels that it always has to be able to enter through, but the interior is more negative than it normally would be at the resting membrane potential. It's negative 75. So sodium is actually being pulled in to a greater degree. So once those voltage-gated potassium channels close and the interior is negative 75, potassium is actually being pulled inward to a greater degree, so it's leaving at a lesser degree, and sodium is being pulled inward to a greater degree. So it's entering at a greater degree because of the stronger negative electrical driving force. So what happens here is that sodium temporarily will actually enter into the Hillock region at a greater rate than potassium will leave. And that means the cell will actually be gaining positively charged sodium ions. It'll be gaining more positively charged ions than it's losing, and that'll cause it to depolarize. And then it'll depolarize and back to negative 70. And then once it gets back to negative 70, right, it depolarizes by 5 millivolts. By making the interior more positive, a more positive interior won't pull sodium in to quite as great of a degree, so the rate at which sodium enters will decrease a little bit, and it won't pull potassium backwards to as great of a degree, so potassium will begin to leave at a little bit of a greater degree, and then you'll get back to the true resting membrane potential, right? At negative 70, you'll be back to the point where potassium is leaving at the same rate that sodium is entering, and you have truly, at that point, returned to the resting membrane potential. And that's what this particular graph shows you. And since this same exact process plays out in every region of the axon, you could say that this graph is applicable to any region of the axon. But as I've said many times, I think the hillock is the easiest of all to kind of imagine. So that concludes the part of this video series which explains how to comprehend this graph. With that said, this graph is often used to explain what are called refractory periods. There's what's called the absolute and relative refractory period, and that is what will be covered in the next part of this video series. You'll be able to find a link on the screen as well as a link within the description if you are interested in understanding how refractory periods relate to this graph.